Second figure is Professor Ovidio Montano from the University of Connecticut. So the title of the talk is Untitled Geometry Shrinking Ricci solitons. So let's welcome.
Thank you very much for the invitation. So this is my second week here, so I'd like to express my gratitude for the invitation for the whole program. It's been a lot of fun, both in the lectures and outside the lectures. And so here I will sort of continue some of the things that I've talked about in the mini course, but on the other hand, I will review some of those things as well for those who are interested and were not here last week. Some of the results have already been mentioned by Detang in the previous talk, so I'll go quite fast over those. So this is just a definition which you've seen in the previous lecture, and I will assume everywhere that, and when I say shrinking Ricci soliton, I mean a gradient shrinking Ricci soliton, and I will assume everywhere that there's a smooth function for which this equation is satisfied. And the manifold will be complete non-compact. So to be sure from the beginning, that's the only part we're interested in for now, complete non-compact shrinking Ricci solitons. So the reason people study them is because they play a role in the Ricci flow, and they are self-similar solution, meaning that the flow is given by diffeomorphism and scaling. That's well known. It's a special type of ancient solution, and so people have studied those this soliton. So here is a typo. In relation to, say, for example, in relation to type 1 ancient solutions, or type 1 singularities to be more precise. So for type 1 singularities, here M is compact. This is the only time when M is compact in the talk. So if you have a compact type 1 singularity and you rescale it in this way, so that it's still a solution of the Ricci flow, Sessum in the compact case, Neighbor in the non-compact case, and Enders-Müller topping finishing the non-compact case prove that this will converge to non-flat gradient shrinking Ricci soliton. So that's one important reason why we study them. But in general, ancient solutions are modeled at the geometry of ancient solutions modeled by shrinking Ricci solitons. So they are quite important. And just as an aside, there's another important reason going back maybe 30 years ago or more for studying Ricci solitons is related to this Ricci F tensor that Detang talked about earlier. And originally, Bakri and Emery introduced this tensor, Ricci F, to prove a log Sobolev inequality. So the Gross-Stam inequality in Rn says exactly this. And if you want to generalize on a Riemannian manifold, it's a fact. It's a wonderful fact that you can do it as long as you assume a lower bound on this tensor. That's easy. And then the inequality is exactly as this one with exactly the same number. Everything is the same where you replace the weight by F. And you've seen in the previous lecture that in general, this weight F behaves like something like this for shrinking Ricci solitons. So basically, it's a very neat result. This is a generalization of this because when you take F to be quarter distance square, you get exactly the previous result, right? So that's an important. I mean, this is one moment. Not the first moment, but one moment when this curvature was introduced, and it wasn't Ricci flow. It was related to functional inequalities on manifolds. Ricci flow came later. So the geometry of Ricci solitons, very quickly, Detang did a wonderful job and already talked about this. He didn't mention the lower bound. So I should say we kind of have a good understanding of the geometry when R is large. So the volume of large balls is understood, and the constants, like he said, are controlled in almost satisfactory fashion. So this is the lower bound. This is Jiaping Wang. So I think everywhere I mention Wang means Jiaping Wang. It's we've done some results in this in the last few years about Ricci solitons. So this is usually for Ricci non-negative. It's called the Yao inequality or Calabi-Yao inequality, and our proof is nothing like that. So we don't use any of those ideas. Actually, we use the previous inequality, this one, and kind of use the Perelman strategy to get volume lower bound. So basically, like in his non-collapsing theorem. But it's a huge difference between that setting and this, because he does it in the compact setting. So he has a tau here in front, and he works with that. So it's in terminology that's called log Sobolev at all scales or something like that. And for us, the scale is fixed, so you can't really immediately do it like he does it. So actually, for that reason, we can't get the volume of the unit ball bounded by a constant. So we can't get really that statement. We can only get for large balls, because we're not assuming anything in addition. We're not assuming curvature bounded or things like that. So we're just doing it from definition of solitons. So no curvature assumptions. The upper bound, originally proved by Huaidong and De Tang, using using a level set proof, a level set argument, as mentioned by De Tang today, can also be proved. So that one can be proved with comparison geometry. So that one follows by the usual Bishop-Gromov kind of argument. But you can't get comparison. So just the upper bound. So it's again, both are sharp. So as you can see from examples, they're cylinder or the Gaussian soliton, which means these two are sharp, and they have fundamental group, finite fundamental group. So these are some results about the geometry, and since I'm interested in asymptotic geometry, I mention only this. There are many others, but these are more related to the asymptotic geometry of Ricci solitons. Besides that, there's some useful identities, and I mentioned this in the workshop. I mean, in the mini course, I'm just mentioning them again. I'm sure everybody in the audience has seen this, at least without this here, because these are because of the rescaling in the soliton, the dilation. But without this, it's just the Ricci flow identities. These come from the dilations. And you have this, which are not really seen in Ricci flow. They come from Bianchi identities. So you just use the soliton equation, apply Bianchi identities, and you get that. It was observed by Binlong Chen in a much more general setting, like for ancient solutions, that they always have scalar curvature non-negative. And in fact, it's even positive if you don't assume, if you rule out flats. So let's just assume from now on that it's not flat, and so scalar curvature is positive. That's a good information, because as you will see later, often you want to divide by scalar curvature. So this allows you to divide by scalar curvature, and that's extremely useful. And you've seen this here in the previous lecture. So basically, the fact that scalar is positive and you have those identities allows you to say that the function, the potential function, grows exactly like on that Gaussian, like distance square over 4. So this is again extremely useful, because now you can use the function in this function f in cutoff arguments. Usually you worry about controlling the Hessian, controlling of the distance, controlling the Laplacian of the distance. Now you don't have to worry about those, because the Hessian of this is given from the soliton equation, and the function itself is like a distance function, right? So as mentioned before, the lower bound, it's kind of a interesting result that the lower bound does not require soliton. It just requires a Ricci lower bound. So that's perhaps it's not really obvious, but it's true. Like I said, this is really useful because now you can cook up a lot of test functions. So that's different, say, from Ricci flow, where you don't have such a function and you don't know how to. I mean, maybe you can think of test functions or cutoff functions in terms of the distance, but they don't always behave very nicely. This one, the function f, for example, satisfies this equation. So by Laplace f, I mean the weighted Laplacian. So it's the Laplacian which is self-adjoint with respect to the weight e to the negative f. So it's a Laplacian that is defined by the weight. So 1 over f is a good function, verifies this equation. So Ben Chao, Peng Lu, who's here, and Bo Yang, they observed a very important inequality that not just scalar is positive, it's actually bounded below by a quadratic, by a function which decays quadratically, by constant over f. That function, this decays quadratically in the distance, as mentioned here. So if it's non-flat, again, I'm assuming non-flat. And the name of the game is just you look at the equation for S. This comes from the previous slide. So you look at the equation for a scalar. You have a test function here which is almost equal. Then you plug in and use maximum principle. Actually, that inspired us to prove the following theorem. This was a couple of years ago. This proves that in any dimension, if you know positive sectional curvature, then the manifold is a compact manifold. So there is no non-compact shrinking Ricci soliton with positive sectional curvature. This was the result. Perelman proved it in dimension 3. Neighbor generalized with Perelman proved it if it's non-collapse bounded curvature, and then Neighbor generalized in dimension 4 if the curvature operator is bounded and non-negative. So curvature operator bounded and non-negative. So our result is in any dimension. It's a different kind of strategy. I mentioned this during the mini course, so perhaps this part of so far I went a little fast because of that. So the way you prove it, you just look at the equation for Ricci, just like we did on the previous slide. Right? Here we looked at the equation for scalar, got an inequality like this, got the lower bound. So we do the same thing for Ricci. Now we can throw this away. Before there was a Ricci square for scalar, so that's why you throw it away. Now there's a Riemann Ricci. Normally you can't throw it away, but if sectional is positive, you can. So you can throw this away. You get an inequality. This is not smooth, so you get it in the sense of supports. But again, you have this is not really equal. It's with some lower order terms that for today's purpose we ignore. Then we get the lower bound. It's exactly the same proof as before. So by Ben Chao, Peng Lu, and Bo Yang. Once you know this, because the gradient of scalar curvature is given by the Ricci curvature in this direction, you essentially get a derivative of scalar to be bounded below. So it's a small bound, but if you integrate that in distance, it becomes scalar becomes huge. It becomes unbounded. That's all we need. So scalar becomes unbounded. So we have this already seems like you're getting somewhere. You have a manifold which has positive sectional curvature, but the scalar curvature is unbounded, right? So you know that should be a problem. And in fact, we don't need to worry about that statement. We can just use more Ricci soliton identities. like integrating this over a ball, and you get the average of scalar curvature cannot be too big. So then it cannot be too big, but actually scalar is big. So that's a problem. This is not a contradiction argument. So it's unlike Perelman or unlike neighbor, where you assume by contradiction they're non-compact, then you study the geometry at infinity, then come up with a contradiction. Here we don't do that. We just say if these are the equations and sectional is positive, then we integrate it. We get the upper bound for R. That's all. So we get an upper bound for R. So unfortunately, this does not give us a diameter upper bound. So the Tang mentioned the result that we proved maybe earlier. That that the previous result we proved was that if it's compact, if it's a shrinking Ricci soliton compact, we want to know, is there a universal diameter upper bound, like depending only on dimension, say. And we were not able to prove it. We proved that if its injectivity radius is bounded below, then the diameter is bounded above. So which is strange. You need to assume injectivity to get diameter. So here we can't get any better than that, because this epsilon, I mean, this is dependent on dimension. This epsilon, unfortunately, depends on, it's this epsilon, which depends on the Ricci lower bound on a fixed compact set. It's a maximum principal proof. So basically, our diameter upper bound depends on what happens in a fixed compact set. So again, kind of like local implies global. So it's more or less the same flavor. You need to know what happens in a fixed set to control the diameter. But the result, as said here, actually with again Bin-Long Chen's result, Hamilton-Ivy type estimate in dimension 3, it does imply the classification of 3D shrinkers. Previously proved partially by Perelman. He assumed kappa non-collapsing bounded curvature, which then removed by Ni, Wallach, and Kao, again Bin-Long Chen and Zhu. So this is one result where there's no asymptotic geometry yet, but it tells you that if you want, I mean, now you have to study things, I mean, solitons which are not positively curved. So are there any examples like that? And there is one in dimension at least 4. So in dimension 3, of course, we classified. We know we have them. But in dimension at least 4, there is such a soliton, and it's constructed by Feldman, Illman, and Knopf. We don't need to know the construction right now. We only need to know how it behaves. It's asymptotic to a cone, so the curvature decays quadratically, and it is not positively curved. So it has negative curvature in some directions, in the potential direction, but it's slightly negative. So it's only it's decaying very fast. So the next question would be, okay, you know positive curved. You know there are examples which are not positively curved. If you can prove theorems, uniqueness theorems for those. So in dimension 4, I think I mentioned this during the workshop, that we have sort of a plan. This goes along the lines like in Perelman or neighbor, that we try to understand asymptotic geometry, see how many solitons in the limit you can get, and then finally to prove that you have a uniqueness. So this is what we can prove for now. This is only in dimension 4. And in higher dimension, none of this, I mean, we cannot do any of this. It may be true, but we have no idea how to do it. So in dimension 4, which I'll explain why the 4, we can prove that if the scalar curvature decays to 0 at infinity, then the soliton is asymptotically conical. So exactly like in this case. And there's work by Kochvar and Wang, which he will talk about on Friday, that at least according to the title, that if you have two cones, if the cone is the same for two shrinking Ricci solitons, then the solitons must be isometric to each other. So that's why I say towards the classification, because at least gives you some hope that maybe, at least in this setting, if you can classify or understand possible cones, then you're in good shape. If scalar is bounded from below, then we can prove it's asymptotic to either one of two possible cylinders. So these two cylinders, or their quotients. So I should say here or quotients of them. What's missing here is what happens. Can it happen that scalar goes to 0 along a sequence and it doesn't go to 0? Or scalar goes to 0 almost everywhere, but there's a direction where it doesn't? That's more likely to happen, but we believe no. We believe such, at least in dimension 4, we don't think that should be the case. And there's some partial, like small little things that indicate that it's not possible to have it, but we don't have a proof for now. So that would be an interesting question to finalize this, to say either or. Right now there's a gap there, which would like to fix at some point. So for the rest of the talk, I'd like to explain very quickly where this comes from and insist on a result which leads to this, but which is true in any dimension. So that result will be true in any dimension, but the applications are in dimension 4. So I'll explain the proof. When I say explain proof, it's of this theorem, which again is Jiaping Wang and myself. So step 1, which was detailed in the second lecture of the workshop, of the mini course, was that if S is bounded, if scalar, so S is scalar curvature. If scalar curvature is bounded, then Riemann is also bounded, and it's bounded by scalar. So C here is not a universal constant. It depends on the upper bound of scalar. So of course, ideally you would like to get a universal constant, but the proof doesn't give us that. So the reason why this is interesting is, again, in view of this kind of dichotomy, we hope to use the fact that if S goes to 0, it forces everything to go to 0. So that should be very special, right? So in that sense, this is interesting because it says when scalar is small, everything is small. And for this, the 4D information is crucial. As you will see in the later part of the talk, if I assume this on an n-dimensional manifold, we can do a lot of things. But this is the part that you don't have it on any n-dimensional shrinker. So this is the part we can only prove in 4D. So, and the 4D is useful because basically by Gauss equations, Gauss identities, and the fact that the level set is 3D of the function is compact, and 3D allows you to express Riemann in terms of Ricci and the derivative of Ricci. So I'm skipping details for this, but it's based on the fact that Ricci determines Riemann in dimension 3, and the level set is 3-dimensional. Then when you go to 4D, Ricci determines Riemann, but there's other terms as well, right? You have normal direction, normal to the level set. Those produce what's here. Then you have to control this. So from here, you have to jump to here, right? So Riemann bounded by S, you only know this. So the next step is to use Hamilton-style computation and divide Ricci by S to different powers. You would like to divide by S squared from the very beginning, but doesn't work like that. You have to bootstrap. You have to do first by S to some power less than 1, then push it to 1, then push it to less than 2, then push it to 2, and so on, because of this term, essentially. So eventually you do get Riemann bounded by S from this idea. then the second step is to take care of the asymptotically conical. That was done mostly in the third lecture in more detail. So it's from the equation of scalar curvature, the fact that scalar goes to 0, you can ignore the last part. So you just get Laplace of S equals S. And since you have a good test function, you get that scalar converges to 0, but in fact converges to 0 quadratically. So it's not just converging to 0, but converging to 0 quadratically. So then you take derivatives, you get matching order for the derivatives, and that implies eventually the result. It's not that part is easy, but this would be if you don't know this result, it's not easy to see why if scalar goes to 0, then the whole curvature tensor has to go to 0, and you have these estimates. That's not easy. So we tried, at some point, we tried to prove this in any dimension. Of course, that would be very interesting if scalar goes to 0 implies such a good control at infinity. We couldn't do it, but what we could do is that if scalar goes to 0 at infinity and Riemann is bounded, then we could prove Riemann goes to 0. Then we can prove it's asymptotically conical. So in any dimension, if we assume in addition that Riemann is bounded, then we could do it. But without that, it's not clear. Or otherwise, if we, to put it differently, if Ricci goes to 0 in any dimension, we could prove it's conical. So if Ricci goes to 0, no other assumption, then we can prove it's conical. But in dimension 4, it's easier. So the last step, which this talk is mostly about, that is what about this S is bounded below. So that's where we use some work by Neighbor. And essentially what you have to do is to show that you take a sequence, you take mg and xk. So you take a sequence like this, xk going to infinity, and if the manifold converges to one of the two cylinders, you have to show it always does so. So if it shows one of the cylinders shows up, then it does show up for any other sequence. That's what you have to do. We prove it for S3. So basically, we show that if S3 R times S2, well, I meant here R times this, R times that. So if R times S3 shows up one time, then it does show for all of them. And that we can prove in any dimension, although it's quite technical if you do it in any dimension. So this is the result I'm going to talk about today. You have any n-dimensional shrinking Ricci soliton, and you assume that along an end, this is in C infinity convergence, that the manifold mg xk converges to this cylinder, and here is g of t in C infinity sense for a given sequence. So there is a sequence xk for which you have this convergence. Then we can prove that actually not only for any sequence this will be true. So there will be no other possibilities. So if you take any other sequence, you'll get the same limit with the same metric. We can prove even more. We can prove that actually the manifold is asymptotic to this cylinder in this sense. So basically, there is a diffeomorphism from one to the other. You pull back the metric, and then it converges to the cylinder metric. K is some compact set. So an end of the manifold. This I should say everything is along an end. Or if you want to make it easier, you just assume it's one end manifold. Then you can prove this. So this is the result that I'll explain in the next 20 minutes. And I think it contains some interesting ideas. And of course, it has application in dimension 4, but it's interesting that it works in any dimension, kind of a uniqueness statement. And those, typically, these are proved by some Loyarsevich inequality. But we don't have that for Ricci solitons. We just do it brute force, like just by estimates. which at least conceptually it's easier. So the notation is that I look at the level subsets of the function of the potential and the level sets of the potential, which are their boundaries. I'll look at the frames which are tangential to the level set and the normal direction to the level set. And then I'll essentially look at this quantity. So this will tell me if I'm close to being space form or not. Right? So this is the tensor that will tell me if I'm close to being a space form. But this is only restricted to the level set. So space form mean on the level set. If the level set is close to being a round, this will tell me exactly that. So this is not the curvature tensor of sigma. So the notation here is not that it's curvature tensor of sigma. It's just the curvature tensor of the manifold restricted to the tangent space of the level set. So there are two basic results in kind of independent. One is the following local derivative estimates. So it says that, which I alluded to earlier, it says that if I have a shrinker and I go far enough towards infinity, and if I know that curvature defined here, so this curvature quantity, of course, essentially in the previous theorem, this is equivalent more or less to Riemann on the level set. So if that is controlled by scalar, right? So Riemann bounded by scalar on an annulus, right? So T is fixed. So this is only true on an annulus. I don't know anything outside. So I have a region in my manifold, an annulus in my manifold, and I know that Riemann is bounded by scalar inside there. And I have a lower bound of scalar on the boundary of that annulus, so on at T naught. Then we got derivative estimates to any order, but in that annulus. So outside that annulus, we are not interested in or we can't have any control. As I mentioned before, we do know this is true in 4 dimensions. So of course, this implies in 4 dimension that it's true. The result is true anywhere. But in higher dimension, I don't expect to be so easy to prove that Riemann is bounded by scalar. So we had to assume it, and again on a fixed annulus, and we got this not on a smaller. So on a smaller annulus, of course, now you know how to do it. You use a cutoff. But I can push the estimates up to the boundary without losing anything. So that's maybe more difficult. So I'll just suggest a proof. And I'll do k equals 1. So only one derivative. Every higher derivatives is the same proof. And I'll do an easier one, which is not s cube. S cube would be what you want, but we'll do just s. Then you iterate this and get s cube. So you have an equation for Riemann, and you'll take this function w, which is the derivative of Riemann squared over s. That's the one you want to control. You want to show that this is bounded, but on the annulus, not outside. So you try to use maximum principle in a way that this again was explained during the mini course. So it's not maximum principle using a cutoff. That would be kind of difficult because that will make the estimate on a smaller set. We want on the same set. So we are going to use a cutoff, but a maximum principle, but for a heat equation, not for the elliptic equation. So to get it on a heat equation, we look at the level. I mean, we look at the gradient flow and transform. Since this becomes
result of forming and the same reduction from, for example, 5 dimension to 4 dimension, and this is what I did.
Yeah, that I don't know. So what I might expect is maybe in 5 dimension, if just use, say, the level set is 4D, and maybe use a sort of Gauss-Bonnet theorem for, I mean, like this kind of argument to get integral curvature bounds for the 5D. but I don't expect this to work like word for word. So maybe,
Maybe a special case.
yeah.
In that sense, I will
Thank you.